Great. My name is Merhnoosh Tahani, and I'm a Covington postdoctoral fellow at the Dominion Radio Astrophysical Observatory with the National Research Council Canada. And I'm presenting this talk on behalf of the Galactic Polarization Science Working Group. So I'd like to also acknowledge Laura Fiesel, who is the leader of the group, as well as Susan Clark and Brandon Hensley, who've helped with preparation of this talk. Thomas we just had two great talks on FYST, and Thomas had presented the instrumentation side at the beginning of his talk. I'll just have a quick recap mentioning that FYST is a 6-meter diameter telescope designed to operate at sub-millimeter to millimeter wavelengths, and it's located at 5,600 meters on Cerro Chajnantor in northern Chile. And the PrimeCam instrument is designed to cover 4.9 degree of the 8-degree diameter field of view of the FYST telescope. And PrimeCam has 7 independent instrument modules, including 350 and 850 gigahertz that are of particular interest for our science group. So FYST, as presented by Thomas, aims to address a variety of questions in astrophysics, including galactic polarization science. And in the galactic polarization science group, we aim to address a series of questions as well, including dust properties and examining dust models and identifying the most successful dust models, characterizing magnetohydrodynamic turbulence, and characterizing the role of magnetic fields in star formation process from cloud to filament to core scales, and mapping the plane of sky as well as 3D magnetic field morphology of a number of molecular clouds. And we also aim to explore the origin of molecular clouds and examine the formation of models that predict formation of molecular clouds. We also aim to map the magnetic fields of diffuse clouds within our own galaxy. And we will accomplish this by 2 surveys. One is the 4,000-hour wide field survey, and the other is targeted deeper wide field mapping of 9 targeted regions. So PrimeCam will have significantly improved sensitivity and resolution and coverage for 3 sigma measurements of polarized intensity. So here we are showing the effective resolution for 3 sigma measurements of polarized intensity, and the white contour shows the wide field survey. The figure to the left shows observations by Planck, and to the right, we see the forecasted observation by PrimeCam obtained by the PISM software. And as shown with the effective resolution contours, we see that Planck at best for 3 sigma polarized intensity had 5 arc-minute resolution, and with the 5 arc-minute will cover almost 1/3 of the sky, like much a bigger area compared to Planck. So if I show these two on top of each other, you can see the improvement for regions that we're not too far off in high latitude regions. So other than this improved observations with the wide field survey, we aim to have targeted observations. And one of these regions that we aim to have targeted observations is the Pyxis cloud, which is a nearby translucent cloud with a relatively high polarization fraction, and provides a simple environment to explore turbulence and cascade of energy, also an ideal laboratory for exploring dust properties and dust composition in atomic gas. So for dust properties, we know that multi-frequency far infrared polarimetry observations in recent years have challenged our views of dust models. For example, Planck observations observed regions of the sky that at 353 gigahertz had significantly higher resolution that we expected from dust models. So they had a polarization fraction higher than 20%. And both Planck and Blaspol in frequencies of 353 to 1200 gigahertz, they showed that polarization fraction is essentially frequency independent. So new models aim to address these challenges. So these models include the models by Gay et al. And Drain and Hensley 2021, which we refer to as AstroDust. So these are two component model versus one component dust models, and they have different implications for life cycles of dust grains and result in different polarized intensity at higher frequencies. So here we're showing polarized intensity as a function of frequency, and with the frequency coverage of FYST or PrimeCam and the resolution and sensitivity, we'll be able to distinguish between these models as we go to higher frequencies. So this observation is for 15 arc-minute observation toward the Pyxis cloud, and we'll have a series of these 15 arc-minute observations. So we'll have a good sample to examine dust models and compare them against each other. So for exploring dust properties, we won't be limited to Pyxis. As we go to higher density regions, we aim to explore dust properties, particularly as a function of column density. In Pyxis, also, we aim to explore the cascade of energy and turbulence from larger scale to smaller scales. And for that, we particularly aim to use dust polarization power spectrum. And in dust polarization power spectrum, since polarization anisotropies are linked or sourced by fluid velocities, this kind of technique gives us a good tool to explore turbulence as well. And because the degree of polynomial for spherical harmonics is directly related to physical scales, we will be able to examine these regions as we go from larger scales to smaller scales, and as they are dominated by different physics. If we go from ideal MHD regimes, for example, to non-ideal MHD. So as we are dominated by different physics, we would expect to have a break in power law spectrum here, and we aim to explore and look for this break. So other than this, many of our targets will also be observed by CHI in C1 and CO, which provide a complementary survey for turbulence and gas kinematics. So for exploring turbulence, other than Pyxis, we also aim to look at the Large Magellanic Cloud, which is a which is a satellite galaxy of our own galaxy, and provides a multi-scale view of turbulence and also magnetic field in star-forming regions as we go from larger to smaller scales. And with the resolution of FYST, we're able to resolve about 8 parsecs. So we'll be able to get down to molecular cloud and star-forming regions to explore the role of magnetic fields in star formation. So for exploring the role of magnetic fields in the star formation process, we also aim to have targeted molecular clouds within our own galaxy. And for these molecular clouds, we will have clouds with different characteristics, different masses, at different evolutionary stages. Particularly, we'll have low, intermediate, and high mass clouds. For low mass clouds, we plan to observe Lopez 1, Pipe Nebula, and Mosca filament. And as we saw in the last talk, Mosca is a very interesting region with high polarization fraction and is a long isolated filament, and it has been debated whether it's a filament or a sheet-like cloud. For intermediate mass clouds, we plan to study Ophiuchus and Aquila, which have been observed in previous observations. For example, Ophiuchus has been observed by the Planck as well as James Clerk Maxwell telescope. For high mass clouds, we plan to observe Orion A and Vela C, which both are of particular interest in the star formation community. So FYST observations will fill the gap that currently exists between the all-sky, large-scale but lower resolution Planck observations and small regions, high resolution ALMA observations. And with these, we'll be able to have an unbiased survey of molecular clouds with a wide range of masses and evolutionary stages. So to explore and characterize the role of magnetic fields in the star formation, we'll explore a number of topics, including exploring the relative orientation between magnetic fields and density structures. For example, like using the histograms of relative orientation, which previously showed that magnetic fields tend to be perpendicular to high column density regions and parallel to lower column density regions. We'll also explore probability density functions for polarization level and magnetic field disorders. And to explore energy balances in the systems to see whether regions are dominated by gravity, magnetic fields. We will determine the strength of magnetic field in the plane of sky with the Davis-Chandrasekhar-Fermi method. And for these targeted regions, we'll compare our observations with the wide field survey as well as with synthetic observations from simulations. So in addition to this, we also aim to combine and study our plane of sky magnetic field observations with the line of sight magnetic field observations using the technique, farther rotation technique of Tahani et al. 2018 and Zeeman measurements. So for example, the technique of Tahani et al. 2018 used Faraday rotation for molecular clouds for the first time to map the line of sight component of magnetic fields in molecular clouds. So they map magnetic fields in 4 regions, but with the current and also upcoming rotation measure catalogs, we will map the line of sight component of magnetic field in a number of molecular clouds. And with these line of sight magnetic fields, using the technique of Tahani et al. 2019 and also recently submitted papers, we aim to reconstruct the 3D magnetic field morphology in a number of molecular clouds. And that would be possible with the Zeeman observations and rotation measure observations that will be made available, particularly possible with Zeeman measurements and rotation measure observations that will be made available by the Square Kilometre Array and the Australian Square Kilometre Array Pathfinder. For example, POSSUM survey with ASCAP has promised a rotation measure source density of 25 to 30 sources per square degree. And which is significantly higher than previous rotation measure catalogs. And with these 3D magnetic field maps, we'll be able to compare these magnetic field maps as well as velocity observations against the cloud formation models. For example, recent papers submitted, as I mentioned here, predict a bow-shaped magnetic or arc-shaped magnetic field morphology that has been predicted in some cloud formation scenarios.
You have 2 minutes left.
So overall, in the Galactic Science Polarization Working Group, we plan to address a number of questions from exploring dust properties and dust models, also characterizing the role of turbulence and magnetic fields in the star formation process. And we aim to provide the community with a multi-scale view of magnetic fields and its role in the star formation process, as well as 3D magnetic field maps of a number of molecular clouds that can be used for comparison with theoretical models and synthetic observations. And with that, I'm happy to take any questions.
Okay, thank you.
Thank you.
So we have time for questions. Marc Sauvage for the first one. So let's keep questions and answers relatively short.
Yeah, do you hear me?
Yes.
Okay. Thanks for this enthusiastic talk. I just wanted to have a clarification on the slide number 4 to make sure that I understand that the plan is really to cover the complete area that you highlighted, or yeah, this one, and to understand what this color bar that you have at the bottom really means.
Mm-hmm. So the plan is to cover this area that is outside the white contour. Yeah, maybe this is not the best representation. And these contours show effective resolution for 3 sigma polarized intensity detection.
Okay. And you, okay, but the fact that the resolution changes is just because you expect this, you always have the same observing strategy, but you expect the signal to be lower and then you integrate
that
spatially.
Is right.
Okay,
yeah.
Thank you very much.
Okay, thank you very much.